Hi teacher, I'm very glad to be here to present our project. Our project name is Inverse Panorama. With the guidance of the Doctor of Philosophy with Văn Tới and our teammates are Phạm Vũ Hiền and Vũ Văn Thi respectively. And now I wanna present our project Inverse Panorama. So in my presentation, I will talk about the introduction, data collection approach, and next is methods, and fifth is result and discussion, and the last one we have some conclusion and recommendation when I did our this project. So the process of checking stock labels on the bottle plays a private roles across the diverse industries to ensuring that these labels are faultlessly and adhered and without wrinkle and buffle and uneven surface. Our objectives here is we want to unflatten the image label, capturing it comprehensively from some perspectives using the inverse panorama. When we start with project, we have to maintain and have some constraint to do this project. That is, the object is restricted as a cylindrical bottle with a simple color background. In the background here, we use the white color. In this case, is white color. The numbers of the viewpoint around the bottle is 4 or 6 frame. So let me talk about the inverse panorama. So in traditional panorama is capturing a wide horizon or a vertical view, but the inverse panorama is is distort and transforming the image and wrapping the sense around the central point. Maybe inverse panorama that propose inverse panorama want to get the surface of the object around the object. Cylindrical panorama are designed to capture a broad horizontal view with the 360 degrees wide, limiting the vertical field of view 4 to 6 view. The camera moves around an object and capturing inward perspective. So by this method that we want to collect data in white background, and we have the can like the orange juice, so the background was informally set to white. The camera was securely positioned in a place, and cylindrical can was rotated around the fixed point, capturing the image of 6 different viewpoint or 4 different viewpoint with the degrees of 16 degree or 19 degree for 4 viewpoint. While the exact angles are very slightly interactive. This value was reasonable accurate. Following this step, we successfully obtained the comprehensive dataset of the cylindrical can. As you can see here in the first row of finger, we have a 6 viewpoint around the can, and the second row is a 4 viewpoints around the can. So our approach in this project, we have initially we have two images stitched together to create a new composite to, create the new the composite image. The composite image will unwrap to minimize the impact of transformation. In here, do we have two images, original image, and then two image will to unwrap to minimize the impact of transformation, and then with users feature extractor like ship or shop or OBs or ORB creator, and then we put with stitching together and with using the feature matching using KNN, and then we by calculating homography matrix by using the Randstad algorithm, and then we use the homography matrix to stitching two images, and we have this one here in the the green picture, green shape here. Okay, here's the green shape is the image stitching, and then with the unwrap, then the output image we compile three transformation and three state. Image one stitch to image two, image three stitching to image four, and image five is stitched to image six. And then we have the output image that's stitching six image together. So our methods in we using this project we have I will present step by step. The first step we unwrap the cylindrical object. The first thing we get mass of object by using the traditional image processing. We get the mass of object. The white pixel here is a mass of objects, and the black pixel is background. So the next step we want to find the source map by getting after having getting mass of objects, we want to find the 6 points of corners top and bottom. So the first step we need to detect 4 corners in the map. The idea here is to detect the white pixel, the first white pixel in the map. Instead of iterating with the column and rows, we run along the diagonal. Here you can see the green lines like a diagonal lines. Anytime the green lines jig to the objects, and anytime they miss a first white pixel, it will assign the corners of the object. As a result, we got the A, B, A, C, D, F points corner. However, our purpose is to get coordinates of 6 points. The bottom here's the 6 point we need to allocate the B point and the E point in the cylinder. The coordinates along the 6 axis is B and E point can be calculated by means of the A's and C's x coordinates, and also with the E point is a means of the D and F's x coordinates. We plot the x coordinates of D point with the F point and divide by 2. So which which is the 3 point A B C, left, right, and top, left, right, and top. Um, we compute a set of evenly distributed points on an ellipse. First, we determine the ellipse center by averaging the left and right point. It's easy to calculate the center of an ellipse shape, and then we calculate the length of the majors and minors axis using the equivalent distance formula. And here, the angular step, which is measure the angles, yeah, the measure the angle of average the angles of between two consecutive points in the ellipse is determined based on the orientation of the ellipse shape here. So you want to calculate the delta. The delta, we need to know about the e values in the e axis in top and minus to center. If greater than 0 is the delta with the pi divided by n. N is the number of points that we test in the math. So next, we use the original formula to calculate the coordinates of x is a point in an ellipse based on the parametric equation analysis. The parametric equation of an ellipse is an ellipse is with a semi-major A and semi-major B, and angle and a phi. Phase measure radian. As you can see here, x is a multiplied with cost delta. The delta we calculate the first slide by the formula in the previous slide, and so by apply this equation, we got the mass that contain many points. And this point we will use to unwrap this cylindrical cam. The object here. Here is the destination map. By having the mass in the previous step here, we calculate the destination map. That's use this equation is by A plus C, this equation, and similarly the average width is obtained by taking the average of two distance and multiply by fees divided by 4, and the step and as you can see in here, let's get the coordinates of the in x-axis in the point A and minus the point C by get the absolute value plot with the these minus f. Yes, here these minus f, and we get the means of two distance here from here to here and from here to here, and so get the width in the destination map, and by similar to computer the height of the destination map. Let's use this formula. Here the destination map. Here's the original image that will collected data, and then by apply a few traditional image processing and unwrap cylindrical object, and we got the unwrapped image with 6 point viewpoint. After we have the six viewpoint, and we have unwrapped image, and we need to detect key point in each image. By applying the shift, we apply shift in here to detect the key, to detect detecting key points and descriptor in an image. Shift in invariant translation, rotation, and scaling transformation. In image domain, it's robust, moderate perspective transformation, and uh, yeah, the advantage of shift algorithm is very useful to in practice for image stitching and object recognition under a real-world condition. So the shift image, the main shift image, the shift algorithm is to the process of computing the keyboard, the main idea to computing the keyboard and descriptor as involves analysis, involving analyzing the intensities of image around a specific location of interest. These interest points are identified by finding extreme points in the scale space representations called the difference of Gaussian, or you can say the DOG in short, pyramid. So here is the main idea that we want to detect this keyboard. In our presentation, I'm not deeply focused on this this algorithm. I will show our result and our experiment that we want to talk about. And before we have a keyboard is the X image. The next step we want to matching X keyboard together. The keyboard which is matched between the fair two images are found by using KNN algorithm. However, a few case, the first and the second closest match can be extremely nearby, which can be a result of the present noise. Here, the present noise and present noise. However, present noise and such as in such case, the ratio of closest to second closest distance is considered. Such ambiguities are discussed if the calculated ratio greater than the threshold values of h 0.8. It has been statistically observed that the 29th procedure eliminates around the 19% of false matching, which is affects improves the overall performance of the algorithm. So in this slide, our finger here, we apply the flange matcher to find the matching keyboards. And in next, in also we have two methods that we want to survey that we apply to brute force matcher in to matching keyboard test. And as you can see in this finger, there are lots of lines, but it's very messy and it's hard to see. It's hard to see. There's a lot of I know slants or the diagonal line. Yeah, the diagonal line. But I want it to want as many horizontal lines as possible. That's so that's so the keyboard have matches it together correctly. Yeah, if you want to the horizontal line then that matches the two images, as you can see, A's which matches like A's, but the A here is written wrong. Um, is wrong matched with the M pixel in here. It's an incorrect match. So then these variable matches will be used to find the homography matrix. Finally, the second image will be the wrap perspective according the first image by using that homography matrix. So, as you can see, this finger, I will talk about a problem is a bit in the previous finger here. There's a lot of matching line and unmatching line, but yeah, the matching line is very messy. So the manually we have a manually incorrect matching here. The manually incorrect matching out of the our observation, and there's a name that is given to these unmatched pairs. It's called the outlier. Why the incorrect ones are called inlier? So we want to we want to want to when matching we have to inliers and outlier. So the inlier is good. It's good to find the homography matrix, but there's many outlier. So the outlier is bad for finding homogeneous matrix, homography matrix. So how can we use the degrees linear transform? The dynamic linear transform is not good by using you in this case because it has many constraints and restrict such as the 3 points map is not in the straight line, um, or if there's many outliers in the finger here, in the finger matching. So this it could be the it make the DLT, the diagram linear transformations get the wrong result or incorrect homography matrix. So our purple and what solution to can robots need the area? So it is ransacked. Yeah, it's finger here. We see that. So we see many areas appear in the match image internally. Is this make the result? It's making the result when using the diagram linear transform methods get bad. Therefore, we're using the ransack algorithm to solve this limitation. Here is the homography that we apply ransack and we solve the inliers matching in here. That's very good. And then we matching two image together, and the right hand side finger is a result. It very clear and it is good, really good. So to finding homogeneous, I have two pictures about by using the diagram linear transform. It gets a worst result, a bad result. Two images can stick together, and when they are unwrapped, yeah, the finger is very bad. But when using the ransack algorithm, and to find the homography matrix, this transform image here, the image transformed, the transform image is really good, but very good and better than the DLT method. So here is our result that we use in our project. Is the final stitching with 4 viewpoints. We compiled on 4 and 6 images and pass them to result by 5 motion image, and then we stitch together. But in with 4 viewpoint, the panorama image is really get very bad, and so you can see we also survey the ratio when we want to cut image in both sides, in the left and right. You want to cut the image in here to here, and we'll survey the ratio, the optimal ratio that we use in our report. And the row here is a real, it's a 5% of the width, and it's a 10% as a 13%, and is a 12%, and we get the with the ratio of 30%, we achieve the best performance. This therefore we use this ratio to investigate other image fair and obtain results. So in the figure here, here is sitting two image. Here's a difficult scenario. We stick two image, but with the ratio test, we get a good result. In general, when performing image with the cut ratio of the 12%, it generates a good result. However, when using the ratio in consecutively connect to 6 point, so 6 image with 6 viewpoint, the result is not expected as shown in this figure here. So after our result here, we want to show the image after stitching two image. Image here is a very good two image with stitching together, and they are performing in very good and clear. And so here we apply the, so in here is the final stitched image. After stitching, we can see that the images are able to match each other, but after merging them all, we see that there's some error in the last corner, and we can see here there's some black edge in here. This can be understood that the homography matrix have not achieved the expected result. So we want to this point here, we crop it in here. So we want all the image is fused by the mask of label and the inverse panoramas of the surround the cam. And so we have some conclusion and discussion. In study focused, we conducted data. We have conducted the data collection and utilized image processing methods to create an improved panorama. With the viewpoint dataset, we experiment with a dataset containing 4 and 6 viewpoints for the study. And the performance assessment, the use of diverse methods evaluate the inverse panoramas models performance. Result in the 6 viewpoint, we see the satisfactory result with the 6 viewpoint and demonstrating feasibility. But we have some challenges in the 4 viewpoint. Required further research. We need more further research, especially to stitchings or processes that the factories result with the 4 viewpoints. Limitations, fixed limitation. We have some limitation in our project. The first thing is fixed background. Observation limited, especially fixed and monochromatic background, and work best with distinct object background color contrast. The dataset adaptation, the tailored approach to specific datasets, adjusting parameters necessary when applying the method to the different data. This is our limitation, and also production optimization. But engineering can frighten the algorithm for production, optimizing the performance and reducing sensitive to noise. The challenge in our project is stitching. Difficulties controlling the cut percent during the stitching, influenced by humans' observation, and significant limitation in methods. Here, by we got this perfect image, but we need to cut image by human and ourselves ourselves view and ourselves personal by personally cutting. We don't cutting alternative automotive. We use this will cutting by here we cutting during stitching and influenced by human observation, and our observation is a significant limitation in our method. And limited object shape, we express the cylindrical objects and methods not expected extend to object with diverse shape and which are the sphere or the cycle object, 3D cycle. I don't know, maybe gets a bad result, and our object will apply into specific object. This is a cylindrical object. And the last thing I want to thank everyone to hear and hearing my presentation, and thank you teachers so much. And I would like to thank to Dr. Tới to guide and give me some experiment to do this project. Thank you so much. Thank you everyone.